The fourth video of this lesson on 3.2 is evaluating logarithms that are natural logarithms. Natural logarithm is a base E logarithm, so one of the things we're going to have to get familiar with and comfortable with is when you see the natural log of some number is the same as log of base E, and we also have to get familiar with E, and E is approximately 2.71828. This approximation was given to us in the prior lesson, and this was found by taking the limit as x approaches infinity of this expression 1 plus 1 over x raised to the x. As we let x get larger and larger, it takes on bigger and bigger values, then this expression will eventually lead to the limit of 2.71828. And it repeats. It doesn't repeat. The 1828 repeats, but after that it's a non-repeating, non-terminating, and so it's an irrational number. This thing occurs quite frequently in nature, and this is the first time that we saw this was on compounding interest continuously. And x stood for the number of times we're going to compound our interest in a given year. So as we increase the compounding periods from annually, semi-annually, monthly, daily, hourly, to the minute, as this got bigger and bigger, as our compounding periods went to infinity, saying they got more and more compounding periods, then this value of our effective rate ended up going towards 2.71828. So because it ends up occurring quite oftenly in population growth or in compounding interest and compounding continuous interest, that is, they call it the natural logarithm, and E is called a natural number for us. Even though it's an awkward number for us to work with, 2.71828, it is very much a part of our mathematics curriculum, and we're just trying to find what this natural number that keeps occurring in the calculations ends up being. This is similar to pi. Pi is a weird number. It's an irrational number that we end up using in circles repeatedly. And we've kind of come to terms with pi. We're going to have to come to terms with E. It's a number that when we look at continuously compounding interest, continuously changing population growth, or we can look at decay as far as radioactive material that is continuously decaying at a certain rate, we're going to have this value of E show up. So because E is an important number and E is going to be a base of an exponential like we have here, if it's e to the y equals x, we should be able to rewrite this in a logarithmic format, which would be a log of base E of our anti-log, which is x, would have to equal our exponent y. So these are true if and only if, and I'm going to replace log of base E with natural log of x equals y. So we have the same relationship, the interplay between natural log of x and e to the y equals x, that we can with all the other bases. Some of these properties, these are repeats of what we've had before. The natural log of 1 equals 0. Well, that's because e to the 0 equals 1, changing it from a log format to an exponent format. This is true because, well, if it's natural log of e equals 1, that means e to the 1 has to equal e. Changing our log into an exponential base, it's a log of base e to the first power equals e. And then we have our other two properties that are holding true on a natural log, just as they were with common in any log base. The natural log of e to the x equals x. Well, that's because if we write this using exponents, it's a log of base e. So if I trade this in for an exponential format, it's e raised to the exponent, because logarithms always tell you the exponent has to equal your anti-log, which is e to the x. And finally, the last one, again, it's more of the same. It's e raised to the natural log of x. That has to equal x. It's the same thought process we had in the other two. This one is already in exponential format, so I can change this into logarithmic format. So I want a log of base e, which is natural log, of the anti-logarithm, which is x, has to equal the exponents, and logs always tell you the exponent, which in this case is the natural log of x. So those rules have been consistent through any log base, and they will always hold true for every log base. The next thing I want to do is just kind of look at the graphs. So you have two graphs. One's for e to the x, the other one is the natural log of x. They are inverses of each other, and because they're inverses of each other, we should be able to graph those with quite a bit of ease to it, I guess. It shouldn't be too difficult for us. So I'm first going to do y equals e to the x. If we do that, then put in values for x and e to the x. Put a -1, that's like e to the -1, which is 1 over e, which is 1 over 2.71828, and so on. If I put in a 0, e to the 0 is equal to 1, just as anything raised to the 0 power is 1. And e to the first is e to the first, but that rounds to 2.7, 1828, and some more stuff. So if I graph those, this is what the graph of y equals e to the x is. -1 is about a third. I'm just saying this is approximately a third, 1 over 2.7 over 1/3. And this is the order pair 0, 1. So 0, 1 is here. The order pair 1, 2.7 is about a 3. And maybe put one more order pair in there just because I need a little bit more definition of a shape. E squared, because that would be awfully close to a 3 squared, since 2.7, 1828 is about a 3, so 3 squared would be 9, so 2 has to be up here close to a 9. And here's what our here's what our exponential growth model looks like with a base e. So to graph our natural logarithmic graph, which means y equals the natural log of x, what we want to do is we want to take and reverse those ordered pairs. So the x and the y ordered pairs get reversed. So it's going to be 1 over 2.7, 1828 gives you -1. 1 gives you a 0, and a 2.7, 1828 gives you a +1. Let me erase that so it doesn't get confused. But all I'm doing is taking these ordered pairs and reversing them, and that means our 3 squared, or the 9, gives you a 2. So we're going to graph these. The ordered pair 1/3 -1, so a third -1, somewhere in there, 1, 0. The ordered pair almost a 3, comma 1. So I go out here to almost a 3, up 1. And then the ordered pair 9, 2 is going to go off the grid a little bit, but ordered pair 9, 2 is somewhere in here. Here's the graph of our logarithm graph. Now, that got a little bit tight just how I drew it. It should not touch the x-axis it gets close to. Some things to think about on your exponential growth model. Can't touch 0. There's a horizontal asymptote on that. So that means when we do the inverse, it's going to have a vertical asymptote. So the concepts of asymptotes switch just like our domain and range do. If it was horizontal, it would become vertical, and vice versa. So how are we supposed to work some of these problems with natural logarithms? Well, you have a natural log key in your calculator, and we're going to have to rely on that for some of the problems. And the first one, the natural log of 32, is absolutely one that we need, because really we're trying to find what is the exponent raised e to get 32. And e is not a kind number. We got that 2.7, 1828, 1828 that never terminates or repeats. So we're going to have to rely on our calculator. So trying to grab that calculator. Let's cancel that one. Clear this out, and we're going to take, this is the one that we're going to evaluate, the natural log of 32. That's what we can do. So we take the natural log, it has its own little key of 32, close the argument, equals 3.46. So we approximate this to be about 3.47. So x is approximately 3.47. One nice thing on this, again, you can check this to make sure it was right. Remember, this number, 3.475735,903, should be the exponent I raised e to. So in behind the natural log is e to the x, and you can put in your second answer, which was our 3.47. If we hit that, it says this is the exponent you raised e to get 32, and it gets us that value. So it's kind of a nice little follow-up on that. In the next one, we shouldn't need our calculator at all. This is one of the properties that they say we should know, that if we take e to the natural log of 4, it should just be 4. So in my mind, I see an exponential base e and a logarithm base e. Since they're inverses, they undo each other, and I'm just left with 4. And that's the property that they're showing you here, the last bullet. And the next problem in 4c, it's the natural log of 1 over e cubed. I'd like to see that as the natural log of e to the -3, using your concept of negative exponents. And now I got another natural log followed by an e to a power. So a natural log of base e and an exponential base e undo each other. They're inverses, so I should get a -3. And what I'm utilizing now is this property right here. The natural log of e to the x is x. So the natural log of e to the -3 is -3. And then in 4d, it's the negative of the natural log of 9. Now this negative is outside the argument. So what they really want us to do is say, okay, what is the opposite of the exponent that you raised e to get 9? But it's very difficult. I'm going to take that negative out. It's difficult to figure out what exponent I raised e to get 9. So what we do to help us with that is we go ahead and use our calculator. and we take the natural log of 9, close your argument, equals, and our value for that should be 2.2 if I round to the nearest hundredth, and that's going to round, so the opposite of 2.20. So the answer for this problem, and then they say find that exponent. The exponent is negative 2.20. That is how we evaluate those functions. So that's our fourth video of this lesson. So we'll stop it here, and we'll move on to the last video.